Welcome back to Tolleson Physics. So we've talked about potential energy, right? Potential energy is energy that's stored in the location that an object's at. So today what we're going to talk about is elastic potential energy. So energy that's associated with things like springs or something else that's stretchy. And so what we're going to do is we're going to remind ourselves of something known as Hooke's law that we looked at earlier. So it turns out the force on a spring is proportional to the spring constant, which is a physical quantity depending on the material the spring's made out of, how tight it's wound, how long it is, so lots of different factors go into that, times the stretch of the spring. And so I put absolute value bars here because some textbooks you'll see that this is indicated as a negative value because the force is pulling in the opposite direction of the stretch. We don't really need to worry about that for our purposes, and actually the AP equation sheet does the same thing. So this is what a graph of force versus stretch would look like for a spring. So notice that it's not a constant level of force, that it's increasing as the stretch increases. And so this actually will inform us as far as trying to come up with a equation that describes this. So if we look at an LOL diagram, so let's assume that we have a spring, that we have a force gauge attached to, and we're pulling on it. All right, so we're pulling on it. So at first, the spring has no stretch. And so if the spring has no stretch, it's not moving. It has no gravitational potential energy and no stretch. And actually, I should specify, we're looking at just the spring as our system. And so my initial energy, there's nothing there. There's nothing there. But what I'm going to end up doing is my hand is going to pull on the force gauge, and it's going to do work on the spring to cause it to stretch. And as it stretches, I'm eventually going to pull it out to a certain length, and I'm going to stop. And so when I stop, that means there's no kinetic energy. And so all of the energy is stored in the spring because of the work I did on it. So if I do my energy of conservation equation, there is no initial energy at all, but I'm adding work into the system, and that will equal the amount of elastic potential energy. Use S for spring, but it is called elastic potential energy. And so remember, work is force times the distance. So I'm going to flip this around. Force times the distance, but in this case the distance is the stretch of the spring. Okay, so what is the force? Well, actually, so what we get from this, it ends up being, and I don't really need to do this, it really ends up being this area. So this area under the curve is actually the amount of work, because notice it's going to be newtons times meters, which is joules. And so the US is actually going to equal, so I'm going to not do that, I'm going to do this instead, that the area is a triangle, 1/2 base times height. So the height is the force at this location, and the height is the stretch. So let's do it that way instead. All right, so this is an actually equation for the stretch if you know what that force is. But you actually don't need to know that. So most textbooks don't actually show this as an equation. What they end up doing instead is taking this equation up here, Hooke's law, and putting it into that right there. So what do I end up getting? I end up getting 1/2, and so now I'm taking k times x times x. So the way that you will normally see this written is 1/2 kx squared. And this is the equation that you typically see when you're dealing with the elastic potential energy of a spring. So to do an example with that, we will have a dart gun, right? So we'll have a dart gun. It has a spring inside the dart gun, and you push the dart against that. So let's say the spring constant is, I don't know, 100 newtons per centimeter. And let's say that we push the spring back, I'd say about 5 centimeters. All right, so how can we calculate how much energy is stored in that? Well, so we're talking about the spring potential energy, the elastic potential energy. So that's 1/2 kx squared. Now this equation only works when you're starting with the spring not compressed at all. So that's actually a consequence of this graph. We're deriving this equation with this graph that starts at 0, 0. So this equation won't work if you start in a different location. So I just wanted to add that caveat. All right, so what do we need to do here? Well, we need to make sure we're using the same units. And what I would recommend is converting each of these to meters. Right? So centi means 1/100th, right? So if I replace, so 5 times 1/100th, that's 100th meters, then that equals 0.05 meters, right? So you can always replace that letter with what it means, and that will always give you that. And then same thing is true up here. I've got equals 100 newtons divided by 1/100th, so it looks funny, meters. But since I have a 100th on the bottom of the bottom, so the denominator of the denominator, that ends up being multiplication. So I got 2 zeros there plus 2 zeros there, so newtons per meter. So those are the numbers that I would use. So the elastic potential energy equals 1/2 10,000 Newton meters divided by meters times 0.05 meters squared. So let's see what that ends up giving us. So 0.5 times 10,000 times 0.05 squared, and that equals 12.5 joules, because it's newtons times meters. One of the meters cancels. So that's a simple way to be able to calculate the energy that's stored in a spring. Now, later we'll be able to use this idea to predict, say, for example, how fast does that dart go out of the gun? Or how high could you shoot it up in the air? So you can use conservation of energy to figure those things out. Alright, the only way to learn physics is by doing physics. So let's take this simple example where we have a spring that we're going to compress. And so this is a light spring that has a spring constant of 50 newtons per centimeter. And we're going to compress it 20 centimeters. So how much energy is stored if we're compressing it from no compression to 20 centimeters? Hit pause to calculate now and unpause when you're ready to see the result. So what we're going to use is our elastic potential energy equation, which is 1/2 the spring constant times the distance squared. And this is always back to an initial distance of 0. And so in this particular case, you really need to use SI units, MKS units in particular, because we're using newtons in one of these. And so newtons is kilograms meters divided by seconds squared. So you have to use those units. So you have 50 newtons divided by centimeters. That converts to 5,000 newtons per meter. You have 20 centimeters for the compression. That converts to 0.2 meters. So when you substitute all of that in, you'll end up with a potential energy, elastic potential energy of 100 joules. All right, so let's do one more example. So now what we're going to have is we're going to have a 1,000 kilogram roller coaster that is going to be stopped using a spring. And that spring has a spring constant of 1,000 newtons per meter. And that roller coaster will be traveling at 5 meters per second when it hits the spring. So the question that I have for you is, how much is the spring going to compress? So let's split this up into two parts. First, what I want you to do is to create an energy bar chart or an LOL diagram. Hit pause now, create your drawing, and then unpause to see the diagram. Alright, so here is what the energy bar chart looks like. So the roller coaster is moving, so it has kinetic energy to start with. The system that I'm looking at is the earth and the car. Suppose I don't necessarily need the earth because I'm not changing height, but I included it. And I actually should have also included the spring because we're going to transfer this energy into the spring. And I actually want to know something about the spring, so I should really add that to my circle in the middle. All right, so now take this energy bar chart and come up with a conservation of energy equation that will allow you to solve for the compression of the spring. Hit pause now and unpause when you're ready to see the results. All right, so here is our energy conservation equation. The initial energy is due to it moving, so it's kinetic energy, and that will equal the elastic potential energy caused by the spring at the end. And then it's a matter of taking kinetic energy equals 1/2 mv squared, and the elastic potential energy is 1/2 kx squared. And so using that, you can solve for x, and ultimately you'll get to a compression of 5 meters. So keep practicing so that you can improve, and we'll see you next time.